Hello and good morning. We are going to continue our notes for Unit 3 Derivatives, the review unit, okay? Um, I said good morning, but I don't know, maybe it's night, maybe you can't sleep, maybe you have insomnia, and the one thing, baby, you've got an itch, and it can only be scratched with more calculus, all right? So let's get ready. Part 2, 2, 2. All right, so we last left off with figuring out what a derivative was. We applied a derivative, we came up with the equation of a line, and we left off right here. Okay, now that we're starting to review and remember what the first derivative is, how do you find the second derivative? Well, first of all, let's figure out, well, what notation could I possibly see that would tell me, that would instruct me to find the second derivative? All right, well, here are the four major ways. They can say y double prime. Okay, of course, this is first derivative, one tick mark. Boom, that's second derivative. There you go. Okay, that means they give you y equals dot, 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 dot. First derivative, dot, 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 dot. Second derivative. Same thing with f of x. If you have a function, dot, 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 dot. The first derivative would be one tick mark, dot, 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 dot. The second derivative, okay? We also said, well, if you get y equals, sometimes they might say dy dx for first derivative. So they would say d2y dx2 for second derivative. Right? Nothing crazy. Now this one here you might say, oh no, it's first derivative. No, Visca, you're wrong. No, I'm right here, okay? This here means take the derivative of something. I'm taking the derivative of the first derivative, okay? If I take the derivative of the first derivative, that means I'm going to end up with the second derivative. Let me explain. Here's f of x. Okay, if I want the derivative of f of x, okay, that's the first derivative, okay? That gives me this, boom, first derivative, okay? Now, if I have the first derivative, but I want to take the derivative of that, that will end up giving me the second derivative, okay? You really don't see this that often, okay? Really, it's these first three, and actually, more so, these first two. So that's notation. So how exactly do we come up with a second derivative? Well, in my explanation here, I kind of told you. I take the derivative of the first derivative, okay? Taking the derivative, differentiating, I can keep on doing it over and over and over and over again. Let me give you just a brief little example, and then we'll get moving probably to more examples. All right, so let's say I'll use y. Y equals 3x to the fifth. All right, well, I can find the first derivative, the power rule. My 5 comes down, and I subtract 1, so I got 15x to the fourth. I can take the derivative of the first derivative. That would give me the second derivative. I bring the 4 down, multiply, that's 60x, then I subtract 1 cubed. Technically, if I wanted to, I could find the third derivative. Put 3 tick marks. The 3 comes down, I multiply, it's 180x, and I subtract 1 squared. And I can keep on going until eventually, in this case, I would end up with 0. But you just keep on taking the derivative of the derivative. Okay. Let's start talking application, okay? Position versus velocity versus acceleration, okay? We can apply derivatives, all right? And this is what your brain should be trained to think. When it talks about position of a particle, movement of a particle, all right? Position is always typically your original function, okay? They'll give you an equation and state that it's position. So f of x is your original equation. Okay, that's position. All right. Although a lot of times they like to say everything's with respect to time, not the variable x. So they say some function with respect to time, and I really hate when they use x of t. I don't know, maybe because it's moving on the x, I don't know, but sometimes they say x of t, where your equation is the function x with respect to the variable t. It's crazy. All right, but anyways, for the sake of not confusing you, it's f of x. Now, how do I find velocity? Velocity is the derivative of position. I'm going to say POS. Hold all jokes. Okay, so it's f prime of x. Whatever the derivative of this is, gives you the equation for velocity. And it's a good thing we just learned second derivative, because acceleration is the derivative of velocity. Okay, now, if velocity is v of t, let's say they give you some velocity. The derivative of velocity is acceleration. However, if they give me the original function, f of x, the derivative of the original function is velocity, and the derivative of velocity is acceleration. So the derivative of the derivative. So acceleration is the second derivative of position. Okay? It's the derivative of velocity, or the second derivative of position. Okay? In this case, this is where I should do the f. Move that over. All right? So, mister, how do I know if I only take one derivative to get the acceleration, or two derivatives? I'll tell you right now, and I'm glad you asked. All right? If they give me velocity and I need acceleration, I only got to do the first derivative. Okay? If they give me position and they ask me for acceleration, I need to take the derivative twice. Okay? So it depends what they give me, how many derivatives I need to use. Okay, it's time to put on our little smart hat. For me, it's a little tiny top hat. Not a big top hat, a tiny top hat that barely fits my head. It like barely stays on, and I kind of put it off to the side of my head, like kind of like at a 45-degree angle, and I got to use one of those rubber straps around my head so it doesn't fall off. That's my smart hat. Anyways, enough about my smart hat. Let's talk about your smart hat and apply it to this problem. A particle moves along a line so that its position at any time is s of t equals t squared minus 4t plus 3. S is in meters and t is in seconds. Okay, a particle moves along the line that its position at any time is s of t. This is my position equation. Okay, that is my position equation. So it says find the displacement of the particle during the first 2 seconds. Okay. Displacement means where it started and where it ended up. So I want to find the position, okay, that it changed during the first 2 seconds. That means from when time started at 0 to at time 2. That covers the first 2 seconds. So I want to know its position at time 0, and then I want to know its position at time 2. That's the displacement. How far did it move? Okay? So S of 0, that means I am going to throw a 0 into each t I have here. So I'm going to end up with 0 squared minus 4 times 0 plus 3. That gives me 3, because 0 minus 0 is 0, plus 3 is 3. Now, my friends, I'm going to throw a 2 into those 2 t's, all right? Because I need to find S of 2. Okay, so now I've got 2 squared minus 4 times 2 plus 3. Okay, 2 squared is 4 minus, okay, 4 times 2 is 8. That's negative 4 plus 3. That would bring me to negative 1. All right? Your math is exactly great, but you haven't found the displacement yet. Okay, how far has it moved? All right, if I was on a number line here, okay, and I started at time 0, I was at position 3. Here's 0, 1, 2, 3. Okay. All right. And I was, and we go to -1, so I'm going to put that here just for poops and ha-has. I started here, right? And my particle over 2 seconds ended up over here. What's its displacement? So how far did it move from here to here? Well, that's 4 spaces. It moves four spaces actually to the left. Okay, so that's how I'm going to answer the question. Find the displacement. It's 4 spaces left of where it started in the first 2 seconds from time 0 to time 2. It's just asking me to find the displacement, not, give some massive explanation. So it's 4 spaces to the left from where it started. That's the displacement. Okay, next. Find the average velocity. Okay, notice that's the question for B. Notice C says instantaneous velocity. Okay, so I'm going to take a moment and back up 1 second here. Derivatives. Okay, it's the same thing as slope. Okay, when I have 2 points, okay, when I have 2 coordinates, I can always use my change in y over change in x. That gives me the average change, okay, of the slope. But when I want to find the slope at 1 point, I don't have 2 points where I can't do y2 minus y1 over x2 minus x1. I need 2 coordinates to do that. When I want to find the instantaneous change, that's when I use derivative, okay? There's a difference. If I have 1 coordinate, okay, at 1 point I want to know that change, I have to use the derivative. When I have 2 sets of coordinates, okay, and I want to find the average change, then I can use rise over run or change in y over change in x. So let's go back to our problem here. Ba-boom. The average velocity during the first 4 seconds. That's from time starting at 0 to time 4. Okay, velocity is derivative, which is slope. I have 2 positions. Okay, I can get 2 coordinates. All right, I can get 2 coordinates. So I'm going to use, because it's average, I'm going to use change in y over change in x. Or in this case, I guess it would be change in s over change in t. So I want to find my y value when s is 4 and subtract my y value when s is 0 all over 4 minus 0. Okay? That's what I'm doing. So basically, in case you just got lost there for 1 second, okay, this is my independent variable, like my x input. This is my output, my y. Okay? Change in x, which is t, at the bottom. Change in y, it's on the top. So if t, or in this case x, was 4, how do I figure out what my y is? Well, I figure out what s of 4 is. And that's what I have right here. Okay? So let's go ahead and do this poo-poo. And I'm going to do this, I guess, mentally, quickly. Okay, if I take 4 and I square it, that's 16 minus 4 times 4, which is 16 plus 3. I end up with 3 minus, we already did s of 0. S of 0 is right here. It's 3. Okay, over 4 minus 0, that's 0 over 4. That means the average velocity is 0. Okay, how do I label velocity? Meters per second. Velocity is always distance compared to time. You're driving a car. It's miles per hour. Okay? Miles per hour. If I was driving, you could say mph, or you could say miles per hour. But for our instance, it is meters per second. That's the average. Okay, that's the average. All right? So, how can someone average 0 miles an hour? If I started, okay, if I started in Rochester, New York, I drove to Syracuse about 2 hours, and I drove back to Rochester another 2 hours. I drove a total of 4 hours. Okay? So you can say, what's your average speed? All right, and you can be like, well, I got to take the, no, speed, it can be directional as well, and we use negatives for direction, like left versus right, which would be positive. Okay, if I say 4 hours later, I'm still standing in the same spot and I haven't moved anywhere, and you don't know, you haven't seen me get in the car and drive to Syracuse and drive back. Okay, I am in a room in my house in Rochester, New York. 4 hours later, you come back and I am in the same exact spot. You don't know I got in the car and went out and came back. So you're like, well, what's my average speed? You're like, well, you went nowhere. Your distance change was 0. So if it's distance over time and your distance is 0, 0 over anything is 0. Okay? If that still throws you off, don't worry. As long as you understand the math behind it, as you understand 0 over 4, if you can plug in the numbers, this is a legit answer. All right? Now, let's find the instantaneous velocity right at t equaling 4. Instantaneous velocity, derivative. It's not the derivative between two, it's not the, the average between 2 points anymore. We want to find the velocity not between 2 points. The velocity right at 1 point, I need to take the derivative. Okay, I'm going to take the derivative of this right here because this is position. Velocity is the derivative of position, isn't it? Okay, so if I take the derivative of position, t squared minus 4t plus 3. So if position equals t squared minus 4t plus 3, let me make sure I wrote that down right. I did. Velocity equals the derivative of position, which is 2t minus 4. Okay, I want to know this right at t equals 4. You could also write it like s prime of 4. That means take the derivative of s when t is 4. You can also say v of 4 because velocity is this equation. It does not matter as long as you plug a 4 into that t. So 2 times 4 minus 4 is 8 minus 4, which is 4. And again, it's meters per second. Bang, 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 gadoosh. Okay? Right at the moment we look at this particle, okay, this is a particle, right? Yeah, a particle moves. Right at the moment we evaluate that particle right at 4 seconds, right at that exact moment. How fast is it going right at that exact moment? It is going 4 meters per second. Good. Good, this isn't bad. Find the acceleration. Okay, at time 4. All right, we can do this one of 2 ways. Acceleration is the second derivative of position. So I could take the derivative of this once, then take the derivative of it a second time. Or I can say, well, acceleration is also the first derivative of velocity. So instead of taking position and doing the derivative twice, I should say to myself, I already did the derivative once. It's this right here. So acceleration is the derivative of velocity. So acceleration, although it's the second derivative of position, that's also the first derivative of velocity, okay? Which means I just take the derivative of this, which happens to be a constant 2, all right? Now, you might say, okay, it's meters per second. Be very careful. Velocity is the first derivative, right? So this exponent to the distance is 1. I just don't write it. Since acceleration is the second derivative, meters squared per second, okay? Second derivative, meters squared, okay? If the derivative is 2, the label should be 2. Think about this. Very early in our educational journey, early in high school or middle school, we learn about gravity. We learn about driving a car that's miles per hour, okay? But what's gravity? Gravity is meters squared per second, isn't it? 9.8 meters squared per second. Do you want to know why gravity is meters squared per second? Because gravity isn't speed. Gravity is acceleration. Okay, it's the change in speed, okay? It's the change of speed. But anyways, acceleration should always have a 2 there. Velocity should always have a 1. Acceleration should have a 2, all right? Now, is the particle speeding up or slowing down at 4 seconds? Oh my goodness gracious, I love doing problems like E and F right here. All right. So how can I tell if the particle is speeding up or slowing down? Okay, I just don't look at velocity, the speed. I need to compare velocity. I need velocity and acceleration, okay, to be able to tell. Okay, then I'm going to put here, I'm going to make a little chart, speed. All right, this is a lot. They're scalar. They're called scalar. What does that mean, their relationship? Think of it like this. It's a lot like multiplication. It's a lot like multiplication, okay? If velocity is positive and acceleration is positive, speed is increasing. Wow, that's a weird plus. If velocity is negative and acceleration is negative, speed is also increasing, right? If I multiply two positives, I get a positive. If I multiply two negatives, I get a negative. Do not take your actual numbers and multiply them and tell me that is the actual change in speed. No. I just care about the sign, if it's increasing or decreasing. So I am going to, boop, acceleration is the change in speed. This. Don't take, look at, my velocity at time 4 was 4 meters per second. My acceleration at time 4 was 2 meters per second. Don't multiply and say, oh, it's changing by 8. No. I'm just trying to get you to make the correlation here between velocity and acceleration. Now, what if the signs are different? What if velocity is positive and acceleration is negative? Well, speed is decreasing. What if velocity is negative and acceleration is positive? It's also decreasing. So if the signs are different, it's decreasing. If the signs are the same, it's increasing. Okay? Just like it's the same relationship between multiplying numbers. Okay? The signs. It's the same thing with the signs when you're multiplying. Okay? Now, at 4 seconds, at time equals 4. Okay, velocity at 4 seconds ended up being, we did that right here, velocity at 4. It's a positive 4, right? It's 4 meters per second. The acceleration at 4, well, we just came up with that. That's a positive 2. Now that is meters squared per second. Now, the speed is increasing because they are both positive. Look, they're both positive, so speed is increasing. However, in a lot of problems on the final, they tell you to explain why. So we're going to explain that right here. Say, particle speed is increasing since both, and you can write this several different ways. A of 4 is greater than 0, and V of 4 is greater than 0. Do not say acceleration and velocity are both greater than 0. The acceleration and velocity where? At 4. You can literally write, because the acceleration at time 4 is a positive value, and the velocity at time 4 is a positive value. But I like to use inequalities because it takes less writing. Bam. All right, there you go. This particle speed is increasing since both the acceleration at time 4 is greater than 0, it's positive, and the velocity at time 4 is greater than 0, it's positive. All right, now, F. At what time, or what value of t, which is time, does the particle change directions? Okay, how do I know, where can I tell when a particle changes directions? Okay, velocity. Change directions, I know I'm going to need velocity. Okay? If, I'm going to write a little note here for you. If velocity is greater than 0 or positive, that means it's moving right. If velocity is less than 0 or negative, that means it's moving left. Okay, this is negative. If you don't like inequality signs, this is positive. Not position, but positive. If it's negative, if it's positive. Okay, now, it is impossible, according to the laws of physics, for something to move right, then move left, or something to move left without right unless it stops first. Okay, let me explain that. If I'm moving right, in order to go left, I need to stop moving right, so I have a velocity of 0, and then move left. Okay, and likewise, if I'm moving left, in order to change my mind and move right, I got to stop, then I got to move right. Okay, basic. So how can I tell? Both of those times, moving right to left and left to right, one thing happened. I had to stop. My velocity had to become 0 at a certain point in order for me to change. So what I'm going to do is I'm going to first find where's my velocity equal to 0, because that's a possible point where I can change direction, okay? That's the whole deal behind finding change in direction, okay? So let's go look at our equation for velocity. We got it right here, highlighted in blue. This is velocity, okay? It's velocity. So let's do this. Let's say velocity equals 2t minus 4. Did I write that down right? I think I did. Yep. So where's that equal to 0? Okay, that's at time 2. Okay, if I add 4, I'm just solving for t here. I get 2t equals 4. And if I divide by 2, so at time equals 2, that's when my velocity is 0. So I'm literally going to put that on a number line. Watch what happens. This becomes really easy. Here's time 2. Okay, here's my time, here's my velocity. I know my velocity is 0 at time 2. I'm literally going to pick a number to the left and to the right of that. That's not the number 2. I mean, the ones that are easy to use. So let's pick 3, and let's pick 0. And I'm going to plug 3 and 0 into velocity. I'm going to see if I come up with a positive value or a negative value. Let's start with 0, okay? 2 times t, which is 0, minus 4. If I evaluate that, that's negative 4. So my velocity is negative here. That tells me I'm moving left on this side, okay? Let's throw a 3 in. 2 times 3 minus 4. Well, that's 6 minus 4. That's a positive 2. I'm positive here. That means I'm moving right. Okay? So, when the time is less than 2 seconds, my particle is moving to the left. Right at 2 seconds, I stop and I don't move at all. Velocity is 0. Then after 2 seconds, the particle starts up again, but it moves right. So what happens at 2 seconds? It changes from left to right. It stops to change directions, okay? Right at 2 seconds. And how do I know that? Because the sign of my velocity changes right through that value of 2. So time is 2 seconds, okay? That's the value of t where the particle changes directions. It goes from left to right. Whew, that was a lot. All right, let's talk about derivatives of trig, okay? I don't know if you guys are going to hear this. I'm going to hear this. My man Jib's here. I don't know if you're going to hear this through the screen. I don't know if they're going to hear this, Leah. I don't know. So I'm going to have to sing a verse for you. Okay? You ready? Do your chain hang low? Do it wobble to the floor? Does it shine in the light? Is it platinum? Is it gold? Do you? Oh, I love that song. If you don't love, I mean, it's playing, and I know you're getting this. Oh, it's just so good. Oh, it's going to be such terrible instruction if you can't hear that song, because now I'm all pumped up for it. But why do I have that? Because the chain rule, okay? The chain rule, okay? What is the derivative of sine? The derivative of sine of u, for any value of u, is cosine of u times whatever the derivative of u is, okay? Keep in mind that that is separate, okay? Notice I put those parentheses there. It is very critical that you realize, okay, it's not the cosine of u times u prime. You're not doing this, okay? The cosine is of u separately. then multiplying that value times u prime. So what I do is I take that u prime, and I like to put that out front. Okay? So it's the cosine of u times whatever u prime is. All right? So what is the derivative of cosine of u? It's sine of u times whatever u prime is, but it is negative. Okay? It should be a negative value. You negate it. All right? And the chain rule, how does that come into play? Okay, this is the derivative, and then I always got to take the derivative of the inside. That's the chain rule, okay? Here's the derivative, but then I got to take the derivative of the inside. That's the chain rule, okay? I'm going to give you a little hint here. Anything that begins with a C will always be negative. Cosecant. Okay, well, that's cosecant of u times cotangent of u times u prime, and you got to negate it. Cotangent should be negative, begins with a C, right? It is. The derivative of cotangent of u is cosecant squared of u times the derivative of u. Chain rule. You got to negate it because it begins with a C. Let's take a look at tangent. The derivative of tangent is secant squared of u times u prime. It is not negative because we are not starting with something that begins with a C. No, there's no mathematical reason behind that. I just make the connection. Okay. Secant of u. The derivative is secant of u times tangent of u times the derivative of u. Chain rule. Do your chain hang low? Okay, there we go. I think you've had enough of that. All right? Keep in mind, we are always doing the chain rule. Okay, whether we realize it or not. This is going to be the song again. This isn't something behind. Oh, there it is. Oh my God. Okay, I gotta get that. All right. So what do I mean? We've always been doing this. The derivative of 3x to the fourth. Okay, we know this comes down. It's 4 times 3x, then 4 minus 1. It's 12x cubed. Okay. We didn't do the chain rule there. We did. Okay, this is our inside. Like, that's our u, isn't it? What's the derivative of x? It's just 1. It's just times 1. So it's still going to be 12x cubed. We just don't do this every time because anything times 1, you know, we don't do it, right? So even though we don't show it, it's still incorporated in every derivative we do. All right? Oh, we're at 32 minutes. Let's see where we're going from here. Oh, we should do this one. We'll do this one and we'll stop here. An object moves along the x-axis so that its position at any time where t is greater than or equal to 0 is given by x of t. Oh, there it is. They call position x of t. That's fine. It's fine. Let's not freak out. Okay. X of t equals cosine of t squared plus 1. Find the velocity and acceleration of the object as a function of t. So we don't need to solve and figure out what the velocity is, a number. We don't got to figure out what the they just want us to find the function that represents velocity or the equation. And then the function that represents acceleration. Okay, so I know that velocity of t is the same thing as the derivative of position. Oh boy. The derivative of cosine is sine. And I'm going to leave some space here. It's the sine. This stays the same. Now, times the derivative of the inside. Okay, forget sine. You are taking the derivative of just this. I know that's 2t. All right. Now, does cosine begin with a c? Yeah. So it should be negative. All right, and there it is. That is the function that represents velocity. All right, now I have to do a function that represents acceleration. Let's go red. Okay, acceleration is the same thing as the derivative of velocity. So I've got to take the derivative of this whole thing right here. Product rule. I'm multiplying two things together, so I need to do the product rule. So, people, it is the first times the derivative of the second plus the second times the derivative of the first. So let's get this thing started. First, negative 2t times the derivative of the second. The derivative of sine, okay, is cosine, and this stays the same, t squared plus 1. But I also got to take the derivative of the inside, which is another 2t, okay? First times derivative of the second, plus the second just as it is. That's the sine of t squared plus 1. Okay, that's the second times the derivative of the first. The derivative of negative 2t is just negative 2. All right, so let's combine anything simple that we can, and let's not overcomplicate things, shall we? Shall we not? Okay, well, I'm multiplying negative 2t times 2t times cosine of t squared. I can multiply these. I get negative 4t squared cosine of t squared plus 1. All I did was multiply these two. It's good. I mean, you can't do anything more. This, I'm just going to put my number out front. So instead of plus, it's going to be minus 2 sine of t squared plus 1. That's a legit acceleration right there. Now, if this were an exam with multiple choice, a lot of the times there's an order to which they write trigonometry. Sometimes they like to write the sine function first. So it might be minus 2 sine of t squared plus 1 minus 4t squared cosine of t squared plus 1. I don't even have to have this parenthesis right here. All right. Okay, how else could they write it? Maybe they'll factor out a negative 2. I don't know why they would, but if it's multiple choice, maybe they factor out a negative 2. You do not have to do this. It did not say simplify. It just said come up with a function. This is a function, okay? This is also a function, and what I'm about to write here is also a function. You do not have to go above and beyond. Give what they ask for. They ask for a function. I'm just showing you the multitude of ways they might show it if it was multiple choice, okay? Let's factor out a negative 2 here. That leaves me sine of t squared plus 1, because the negative 2 is gone. Negative 4 divided by negative 2 is positive 2 t squared. T squared, where'd the t squared come from? Am I okay? Am I okay? It'd just be negative 4. Look at that. I'm getting crazy. In my old age. Cosine of t squared plus 1. Okay, it might be written like that. Okay, they may have factored out a negative 2. Right? Could be anyways. As long as you understand the basic algebra behind manipulating an equation, you are fine. You're in calculus. You should be able to make that connection by now. Okay? This is a fantastic place to stop. We are already 8 minutes over where I wanted to be. But you know what? That first problem with that particle moving left and right and speed increasing or decreasing and change in direction, those are important things to know. Those come up frequently. Okay, they do come up frequently, so I want to do that and get a little bit further ahead. Okay, so I will see you. Part 2 is done. We will continue part 3 as soon as you click next video. And don't forget to like. I never say that. You know, all these videos are always like, don't forget to like my stuff, you know, share. Yeah, subscribe. Subscribe to my button below. I got to start doing graphics and images of... Yeah, thick cake. I gotta just start doing something, you know, where you just like me, send me, please like me. I'm nothing unless you like me. Okay, hit next. We'll see you for part 3. See ya.